How long does it take for a monkey hitting keys randomly on a typewriter keyboard to type abracadabra? Or to type the complete works of William Shakespeare? How many tosses of a coin on average to get 2 heads in a row? Or to get heads tails? And which of these two is most likely to happen first? By Martingale theory and optional sampling, thinking about simple gambling games gives a shortcut to these calculations and much, much more. But what even is a martingale? What is optional sampling? And how can it help us? In this video, I'll answer these questions and more, and I'll use optional sampling to answer this multiple choice question, which only 15% of people got correct. So let's get into it. I'm almost sure. Hello and welcome to Almost Sure. Suppose that I repeatedly toss a fair coin. And before each toss, I'm going to stake $1 that it will come up heads. And if it does, then I win $2 back, which makes it a fair game. And I'll repeat this for every coin toss until eventually a heads comes up. And then I'll walk away. Now, if it takes N tosses for heads to come up, then that means I've staked $1 N times. So that's a total of N dollars. But I've won $2 back from correctly guessing the final head. So I have a net profit of 2 minus N dollars. But this is a fair game, so the expected net profit is 0. So the expected value of 2 minus N is 0. And rearranging this gives that the expected value of N is 2. Looking at this simple gambling game tells us that it takes 2 tosses on average to get ahead. Now, I looked at this calculation and others in a previous video, which I will link up here. But I'll recap the arguments here and include links at the end of this video and in the description, so no need to click away just yet. Or if you do click away, please come back after watching it. Okay, let's look at another example. How many tosses to get heads followed by tails? Here we consider a whole line of gamblers, with one entering before each toss. And when the gambler enters, he will bet $1 that the toss comes up heads, and if it does, he takes his $2 that he wins back and bets that the following coin toss is tails. And then this game ends when eventually heads tails comes up. So let's see what the outcome of such a game is. Here you see all the players that have faded out. They've lost, and there's just one single happy Wojak who has won, and he's the one that correctly bet on heads tails and won $4. If it took N tosses to get heads tails, then N players have entered, each putting $1 in, so N dollars have been put into this game, and the net profit from our team of players is therefore 4 minus N. Again, this is a fair game, so it's got 0 expected value. So 4 minus the expected value of N is 0, so it takes 4 tosses on average to get heads tails. Nice. For our final example before moving on, how long to get 2 heads in a row? Do you think it's the same as getting heads tails? Well, let's again consider our row of gamblers. Each comes in before a coin toss and bets that his toss is heads. If he wins, then he takes his $2 winnings and rolls it over to bet that the next one is also heads. And this game will end once 2 heads come up in a row. So let's see the outcome of this game. Now we've got 2 happy Wojaks. The one who correctly bet on 2 heads in a row has won $4, like before. But now there's also the one who entered on the final toss and has also won, because heads both begins and ends with heads. He correctly guessed heads, won $2 and is still in this game. So $6 in total has been won, meaning that the net profit for the whole team is 6 minus N. Again, it's a fair game, so 0 expected value. So the expected number of tosses to get 2 heads in a row is 6. And similar considerations show that it takes 42 tosses to get heads, tails, heads, tails, heads, or 42 rolls of a regular dice to get 2 6s in a row, or this many key presses for a monkey to type abracadabra on average. The net profit and loss at each step of these kinds of fair gambling game is called a martingale. But what really is a martingale? Well, it's an intriguing word at least. Martingale. It is apparently the name of a strap used to stop a horse from raising his head too high. In fact, the word martingale has been used for various types of straps, ropes, belts, many things, other items of clothing. But that's not much help to us. The word likely comes originally from the Provençal language of southern France relating to the Martigues region. But this obscure etymology is not important right now. So journey back with me, if you will, through space and time to 18th century France. Gambling is a popular French pastime and indicator of wealth and status. The Martingale betting system is well known. After each loss, you double your stake, or at least sufficiently increase your stake to recoup all losses, in order to eventually guarantee a profit. In reality, martingale strategies are a bad idea. They risk large losses. There's never a guarantee of success, but I'll discuss this later.
Bonjour, monsieur.
Oh, bonjour. Okay, let's leave 18th century France behind. Gambling and probability theory have had a symbiotic relationship for centuries, with gambling serving as a source of problems to investigate and a testing ground for mathematical theories. So in his thesis, published in 1939, the probabilist Jean-André Ville, okay, you're going to have to excuse my French pronunciation on these, he borrowed the word martingale when analysing such games of chance. And then later, martingales were popularised by Joseph Dube in the 1950s, who developed much of the mathematical theory. And since then, martingales have grown into a very powerful tool with applications in probability, statistics, harmonic functions, and more. Mathematically speaking, a martingale is, well, it's not the same thing as a gambling game. Its definition might have been inspired by such games, but suppose I was to ask, is Brownian motion a martingale? Is this true? And by Brownian motion, I'm talking about the random motion of a small particle in a gas or liquid as it's battered by the individual atoms. And this is a well-known physical process. It's got nothing to do with gambling. So, well, we're going to need a proper definition that can be used in whatever situation. So, mathematically, a martingale is a type of stochastic process. This is a sequence of random variables, x of t, for each time t. In discrete time, like in our gambling games, time is measured discretely as integers. T is 0, 1, 2, etc. So we have a sequence of random variables. For our process x to be a martingale, then at any time n, the expected value of the next term in the sequence, conditional on all currently observable information, this should equal the present value. Or in other words, the expected value of x of n plus 1, conditioned on all values of x up to time n, equals x of n. This captures the idea in a fair gambling game that at any time n, the expected wealth at the next step should equal our current wealth, so it neither increases nor decreases on average. We do need a technical condition here, and that's that the random variable should be integrable. In other words, the mean or expected value of their absolute values have to be finite. It is possible for random variables to have infinite mean, or undefined mean even. If both the positive and negative parts of x had infinite mean, then the expected value of x, this would be the sum of the expected values of its positive and negative parts, so the sum of positive infinity and negative infinity, and well, that makes no sense. So we exclude these pathological cases. And this ensures that the conditional expectations that we just mentioned also make sense. A simple example of a martingale is a random walk. This starts at 0, and then at each time step it either increases by 1 or it decreases by 1, both with 50% probability. And actually this is the same thing as tossing a fair coin and keeping a running total of the number of heads minus the number of tails. Alternatively, suppose we were gambling and we were betting $1 on heads before each toss. If it comes up tails, then we lose our $1 stake. But if it comes up heads, then if it's a fair game, we get $2 back, so a profit of $1. So the net profit of this gambling game is a random walk. Okay, back to our definition of a martingale. And there's still some loose ends to clear up here. Recall that we conditioned on the currently observable information, which was represented by the present and past values of our process x. Now, mathematicians capture the idea of this current information by the concept of a sigma algebra. This represents a collection of events in our probability space or information. There are technical requirements for something to be a sigma algebra. The complement of any event in the sigma algebra, that should also be in it, as is the union and intersection of any pair of events, or even of any infinite sequences of events. But I'm not going to get hung up on that now. The technical definition won't concern us in this video. So write f of n for the sigma algebra generated by x of 0, x of 1 up to x of n. That's all events which can be observed just using the values of x of 0 up to x of n. This does allow us to tidy up the notation a bit. So instead of explicitly writing out all these expectations conditioned on x of 0, x of 1 up to x of n every time, we simply say that it's conditioned on f of n. So that makes it a little bit tidier. And also note that the observable information is increasing over time. At each step, at time n plus 1, we not only observe the values of x of 0 up to x of n, but also x of n plus 1. So the sigma algebra f of n plus 1 is bigger than f of n. So we have an increasing sequence of sigma algebras, one at each time, representing the events observable up to that time. Such an increasing sequence of sigma algebras, this is called a filtration. Using filtrations and sigma algebras is pretty useful. It separates out the flow of information from the process itself, so that makes the theory more flexible. That f of n is the events observable in terms of the values of x up to that time. This means that it is the natural filtration of x, but we can drop this requirement. We don't need it to be that particular sigma algebra. For example, we could be modeling two different processes at the same time, both of which can be observed, increasing the amount of information. A common situation in finance is modeling stock prices, but then we don't just have the prices of a single stock. We've got loads of information. We've got information on volatility, on interest rates, on currency exchange rates, and a whole universe of assets which can be incorporated into the model. So it's just too restrictive for many applications to only use the natural filtration of x. We can fix this by simply just getting rid of it. So we just cross out this requirement and we have our definition of a martingale. The filtration here is just any increasing sequence of sigma algebras. There is one kind of additional requirement, which is that x should be adapted. This means that its value at each time n is observable at that time. So x of n is f of n measurable. But for martingales, that condition is already implied by the first property here. I mean, x of n is equal to expectation of something conditioned on f of n. This implies that it's, at the very least, it's measurable with respect to f of n. So we already have that property, so we don't need to explicitly require it. Okay, here's actually another example of a martingale, which I just thought of while I was recording this video. And it's election year in the US, as you may know. And the top two candidates are Kamala Harris, did I say that right? And of course, Donald Trump. And without getting political here, what's the probability that, say, Donald Trump will win? There's various surveys and betting sites that publish estimates of these probabilities, probabilities for each candidate or the odds for each candidate. And the progress of these over time will form a martingale. Well, they will do if they're done accurately. And the same is true of the probabilities of any future event, like the odds of a team winning a football match. It follows from the Tower law of conditional expectations that this is a martingale. But imagine you're a member of the football team and the match is about to start and you happen to know that your star player is not performing well. Then, well, you've got some inside information and maybe you know that you have less chance to win than suggested by the odds. Or maybe you're a member of the president's inner circle and you know who's about to drop out of the race, even if it's not been announced publicly. Then the published odds will not be correct to you, and the probabilities will not be a martingale. I hear you ask, what gives? How can it be a martingale to the public, but then to somebody else, it's not a martingale? Well, just look at the definition. It doesn't just involve the process X, it also involves the filtration. And this example just shows the importance of the filtration. The filtration at any time is sigma algebra representing the available information at that time. Someone who has inside information, well, they have more information, so they have a different, bigger filtration. And a martingale with respect to one filtration does not have to be a martingale under another, bigger filtration. The optional sampling theorem tells us that in a fair gambling game, if we stop at a time of our choosing and look at the net profit so far, then on average, it's 0. In terms of our martingale X, this means that its expected value at the random time t equals its expected value at time 0. Let's look at the basic statement. Here it is. If X is a martingale and t is a bounded stopping time, then the expected value of x of t is equal to the expected value of x of 0. Note that we have two conditions on t here. First, it must be a stopping time. But what does that mean? In fact, it has a mathematical definition, which is that the event that t is equal to n is observable at time n, which means that we know when time t happens. And this is an obvious restriction in the gambling setup. We can only walk away at a time if we are aware when that time happens. T can be random, but it must at least be observable at time t. We can't bet on 100 coin tosses in a row, then go back in time to look at the profit at the time it was the greatest, since we don't know when that time is until after the fact. There's another condition here, and that's that t is bounded. And this means that it must be less than some fixed positive time n with 100% probability. Now it looks like a bit of a technical condition, but in many applications this won't actually be true. In fact, it's not true in any of the examples in this video or in my previous video on martingales. For example, the number of tosses to get ahead. It can take any length of time. And maybe with a very small probability to take a very long time, but it's still non-zero probability. You might wonder why we can't just approximate our stopping time by a bounded one and apply the result. Well, we can do exactly that, although it doesn't always work out. So let's modify our statement. First, cross out the word bounded, then insert this new integrability condition instead. The maximum value of x up until time t should have finite mean. If you know the dominated convergence theorem, then you can probably say why this condition is sufficient for approximating by bounded times to work out. This integrability condition is much weaker than time being bounded, and in fact it is indeed satisfied in all the examples of optional sampling in this video and in the previous one. I've spent most of this video explaining that the payoff of a fair gambling strategy has zero expected profit, and how this can be used with some cunning to answer questions about random processes. It's now time to upend this and show that it's all wrong. The expected profit does not have to be zero. Don't worry, all will become clear, and this only happens if we are sloppy and careless. So let's be sloppy and careless. Let's throw caution to the wind, and let's go all the way back to 18th century France and to the Martingale betting system. Suppose we're betting on coin flips. We bet on heads. So if it's a fair game, and then we lose the stake if it comes up tails, and we win double the stake back if it's heads. So start by betting $1 on heads. Actually, the currency in 18th century France was apparently the livre, I think, but I'll stick with dollars. If we win, we have a profit of $1 and walk away. If we lose, then we bet $2 on the second flip. So if we were to win on the second flip, then it would cancel out the first loss and we would have a profit of $1. But if we lose again, then we double the stake again and bet $4 on the third coin toss. And again, this would cancel out our losses so far if we were to win. And then we continue like this. We double the stake every time we lose. Then eventually heads must come up, after which we walk away with a profit of $1. I mean, what we're doing here effectively is taking our loss so far at each point and then staking one more than that on the next coin toss. So when heads eventually does come up, then it cancels out all our previous losses, leaving $1 profit. And yeah, this is a fair game. And we are guaranteed to win $1, free money. Right, what gives though? The expected profit is not zero, it's 1. So why doesn't this contradict the optional sampling theorem? And why weren't 18th century French gamblers all rich beyond the imagination? Well, there is a catch, obviously, and it's a big one. Let's play again. In the example game, we lost 3 times in a row before heads came up. I mean, unlucky, but it could have been much worse. We could lose 4 times in a row, or we could lose 5 times in a row, or 6 times, or whatever. You should start to see the problem here. I mean, if we have a long streak of bad luck, then as time goes on, our stake blows up exponentially. We could lose 10 times in a row. At that point, we are gambling stakes in the thousands of dollars with only a chance of ever winning $1. There must be some credit limit, and if the losses exceed this, we can't continue, so we have to quit. In that case, we have a big loss. After 10 tosses, we've either won $1 or we've lost $1,023, which happens with a probability of 1 in 1,024. Okay, yeah, that's a small probability, so we probably would win. But if we did lose, then it's a big loss, right? Is it really worth risking $1,023 when all we can win is a measly $1? And this is like a lottery in reverse. We could try using smaller stakes to reduce the chance of hitting our credit limit, and then play the game multiple times. Maybe start with a 10-cent stake and play the strategy 10 times in a row. And yes, this reduces the chance of hitting the credit limit in any single try, but also we're taking this risk 10 times over, which increases the chance. So however you do this, if there's a finite credit limit, we can never guarantee a win, and the expected profit will be 0. Actually, that bit's not quite true. You could do a reverse Martingale strategy where we double the stakes when we win instead of when we lose. And all we're doing is just betting our entire winnings so far at each coin flip until eventually we lose everything. So this would guarantee an eventual total loss, which is not a great idea. In the Martingale strategy, let's look at the total amount staked throughout the game on average. This will be the sum of the expected amount staked at the start before the first toss plus the amount staked before the second toss, or after one toss, and then after 2 tosses, and so on. So this is an infinite sum. After n tosses, the expected stake is the probability that the game lasts that long multiplied by the stake if it does. This is the probability of n tails coming up in a row, or 2 to the power of minus n. And then as the stake is doubled each time, it's multiplied by 2 to the n. So the expected amount staked on the nth go is 2 to the minus n multiplied by 2 to the n, or just 1. And when we sum over n, we get total expected stake of 1 plus 1 plus 1, and so on. It's an infinite number of 1s. So that's an infinite expected stake. In the Martingale strategy, expected stake is infinity. And we have a 50% chance of losing any amount staked. So this is bad. It's very bad. The expected loss just before we eventually get ahead is infinite. Now let's go back to the optional sampling theorem. Let's look at the condition here. This is that the expected value of the absolute maximum of our Martingale up to the time should be finite. So it doesn't apply to the Martingale betting strategy. Maybe you thought this condition was just a technical detail which you can practically ignore, but no, it's a real necessity. When it doesn't hold, which it doesn't in some simple cases, then the result does not hold. But as long as the condition is verified, then optional sampling can be applied and everything is good. So the Martingale strategy is bad in practice, since if we enforce a credit limit or anything else which may force us to stop before a win, like running out of time, then we can have big losses. It's also bad in theory because it has infinite maximum expected loss and optional sampling does not apply. So let's leave 18th century France behind along with its dodgy gambling ideas and see some other problems where optional sampling does apply. Daniel Litt asked this question on Twitter. Keep flipping a fair coin until you see 5 consecutive flips of the form heads, tails, 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 heads, or heads, tails, heads, tails, heads. Which is most likely to happen first? In fact, only 15% of people voting got the correct answer here. We can do this with the Martingale method and get the correct answer. Let's consider 2 people, Alice and Bob. A coin is tossed repeatedly, and if heads, tails, 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 heads comes up first, Alice wins. And Bob wins if heads, tails, heads, tails, heads is first. Who's most likely to win? Let's suppose Alice has a team of players, all arranged in a line, and one enters the game before each coin toss. When a player enters, they bet $1 on their coin toss that heads comes up. If they win, then the $2 winnings is rolled over to bet that the next toss is tails. Then any winnings are rolled over to bet that the next is tails, then tails again, then heads. And as soon as they lose one toss, they quit the game, losing their initial $1 stake. Now this idea is similar to the Martingale technique I used earlier in this video and a previous video, which I'll link at the end, and can be used to determine how long it takes on average to type heads, tails, 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 heads. The difference now is that we have another player, Bob. Suppose he does a similar thing. He has a team of players with one entering before each toss. But we suppose that his players bet on heads, tails, heads, tails, heads. That is, they bet $1 on heads, rolling over any winnings to bet on tails for the next toss, then on heads, then tails, and finally heads. Let's play this until one of Alice or Bob's sequences comes up and see what happens. How much does Alice or Bob win? Well, let's play the game. So heads, tails, 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 heads came up first, meaning Alice won. But how much cash did her team of gamblers actually win? Well, there is a player who entered 5 from the end and correctly guessed the whole heads, tails, 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 heads sequence, rolling over her stake each time to amass $32, or 2 to the power of 5. Also, her gambler who entered on the final toss is still in the game. She bet on the final head and won $2, which has not been rolled over yet, so Alice has $34 of winnings. There's also the amount staked, which should be subtracted from a profit, and this is $1 for every one of her players who entered, and is just equal to the number of tosses until the sequence came up. I'll ignore this though, because Bob staked exactly the same amount, and it will cancel when we compare their profits. But what about Bob? His sequence, heads, tails, heads, tails, heads, did not come up, but he still has some winnings here. His final player guessed the final head, so he has got $2 of winnings. Let's play one more round and see what happens this time. Bob's sequences come up. Heads, tails, heads, tails, heads. Let's check their winnings. Although her sequence did not come up first, Alice does have some winnings. Her final player to enter correctly bet on the final head, so won $2 back. As for Bob, his sequence came up first, so he has one player who bet on the full heads, tails, heads, tails, heads sequence and won $32. But his player who entered 3 from the end did correctly guess heads, tails, heads, and is still to roll this over, so has won $8 so far. And of course, as with Alice, his final player to enter guessed the final head and won $2. Let's apply the Martingale technique to this. As it's a fair game, Alice's profit and Bob's profit will be 0 on average at the end. But I'm interested in the difference of their profits, which also has 0 expectation, as net profit is total won minus the amount staked. if we subtract Bob's profit from Alice's, then the stakes will cancel out. And in fact, the difference between Alice and Bob's winnings is a martingale. And more than that, it's a bounded martingale. So the optional sampling theorem applies. The expected winnings of Alice minus that for Bob is 0. But if Alice wins, then we know how much each of the players won in total. We just did this above. And the same applies if Bob wins. So we can split the expected value into terms conditional on Alice winning and conditional on Bob winning. So this gives an expression relating the probabilities, with factors depending on the amount each of Alice and Bob win. For each of the two cases where Alice's sequence comes up first and when Bob's does. And rearranging this expresses the probability that Alice wins as a multiple of the probability that Bob wins. We plug in the values for each of the possible gambling winnings. And rearranging, we see that Alice has a probability of 5/4 times by the probability for Bob, from which we can infer that her probability of winning is 5/9, which is greater than 50%, and Bob has probability of 4/9. Let me just leave you with a question here. Can you give a general formula which, given any two finite sequences of heads and tails, tells you the probabilities for which appears first? There's so much more that we can do. Consider a random walk, for example. This is the winnings from betting on a sequence of coin flips. If we bet $1 on each coin toss, that it comes up heads. So we lose $1 or win $1 on each toss. Then what's the probability that we win $5 before we ever lose 5? Or the probability that a random walk reaches 5 before minus 5? Okay, obviously that's 50% because it's by symmetry. But what about the probability of a random walk reaching 5 before minus 3? I mean, that must be less than 50% because 5 is a bigger number to reach than 3. But using Martingale theory, then we can say that the exact answer is 3/8. Probability of reaching 5 before minus 3 is 3/8. And let's say 5 before minus 10, that would be 10/15 or 2/3. Here's an exercise you can try if you like. Can you prove these results just mentioned by applying the optional sampling theorem? And using the correct method, it just drops out pretty easily. For a more difficult exercise, what is the expected length of these games? That is, what is the expected time for a random walk to reach 5 or minus 5, or 5 or minus 3, or 5 or minus 10? I should say this is a difficult exercise. It's double-starred exercise, so I'll give you a hint. Think about the squared values of the random walk. What do you need to add or take away to make this into a martingale? But before attempting that, please make sure you like and subscribe. Even if you don't want to attempt to answer my questions, you've stuck with me this long, so you should like and subscribe anyway. Okay, I'm optionally stopping now. If you haven't already, you can click on my earlier video, which will appear up here somewhere. Bye.
I'm almost sure.